Here is an example of a simple hypothesis test where we're looking at two proportions, right? Anytime you're running any kind of analysis, you're going to have to identify what's going on. And you can identify that this is a proportions question because they give you counts, right? They tell you 150 patients were treated with oxygen and 148 were given a placebo. They tell you that among the 150, 116 were free from headaches, and then among the 148, 29 were free from headaches 15 minutes after treatment. Then we identify kind of the question. Here's our significance level, 0.01 significance level. Test the claim that the oxygen treatment is effective. So we're basically just asking the question that between these two groups, did the people who were given oxygen have headaches less frequently? So it's really just comparing proportions. So the first thing we want to do is test this claim with a hypothesis test. So we want to set up our hypotheses. The null hypothesis, right, is just that the proportion of sample 1 is equal to the proportion of sample 2. And then the alternative hypothesis is that one of them is bigger than the other. P of 1 is bigger than P of 2. Now we could set this up differently depending on what we name our groups, and which group is P1 and which group is P2, and whether we're asking did the proportion of people who were free for headaches go up, or you could kind of look at it the other way and look at the number of people who had headaches, was that lower? Right? I mean, it's really you're asking the same question, but because the information was given to us in the question as the number of people who were free from headaches, then we're going to let our P's or proportions be those who were free from headaches. So P1 is going to be the oxygen group, and P2 is the placebo group. And P1, because we're talking about the proportion of people who were free from headaches, that's simply going to be the number of people who didn't have headaches divided by the number of people who got the treatment. P2, number of people who were free from headaches, divided by the total number of people who got the placebo. So we can calculate each of those to figure out what's going on with our p-values. Okay, so we've got our p-hats, right? Both of our two proportions from our samples. Then we've got our formula for our z-score, which is we're just looking at the difference between our p-hats minus the difference in our hypothesized p's, which in this case, because our null hypothesis is equal, these two are equal to each other. So of course this piece here is just going to be 0. And then we've got this p bar q bar over n1, p bar q bar over n2 thing in the bottom. And you have to remind yourselves that p bar is just the pooling of the p's, right? It's the pooled proportion. You're basically putting everything together and saying, what's the total number of successes over the total of both samples? So in this case, we have the 116, right, that were free from headaches, plus the 29, so that's the total successes, and then the two sample sizes is the 150 plus 148, and that just gives us an overall, you can kind of think of it as an overall p-hat. It isn't, right, because it's p-bar, but it's kind of giving us an overall proportion. If we do the work, this is everything we get, right? Our p-bar is just basically the average of all the successes, and that ends up being 0.4866 if we round, and then we do 1 minus that to get q-bar, and we get 0.5134. Again, we're rounding. Plug all that into the formula, and again, you're rounding on top of rounding. That's the one problem with kind of doing these things by hand. You get a z-score of 9.97, and that's, as we all know, way out there in the tail. So we're definitely going to reject this no matter what level of significance we put this at. But if you wanted to check your z critical, right, the one based on this level of significance is 2.33. And because our z-score is bigger than that, right, we reject. We could also calculate the p-value based on a z-score of 9.97. And that p-value is going to be really, really close to 0, which is, of course, less than 0.01. And we reject based on that as well. Now, if we want to do this with technology, it's a lot easier in either the calculator or StatCrunch. So here's how we can do it in the calculator. You go stat tests, and we're doing a 2 proportion, right? Z-test. And now you just need to tell it everything you know. X1 is the number of successes from the first set of thing, 116. N1 is the sample size. X2, a number of successes, right? Sample size for the second set. We need to make sure we change our alternative hypothesis to the correct thing. The way we have it set up here, right? P1 is the oxygen, and we're thinking that should be better. So that's going to be P1 is greater than P2. Calculate. Here's the same z-score we got. Here's p hat for 1, right? See that? And then there's that one. This here, 0.4865, that's something that we don't really need to deal with. If you scroll down, it gives you the rest of the bits and pieces of N1 and N2. But you can see that we got our P, that's our probability, is e to the negative 23. So like I said, really, really close to 0. You basically have, 22 zeros. So we know we reject. StatCrunch, just as easy. We go to stat, proportion stats, 2 samples with summary. And the same thing, we have to type in all the information that was given to sample 1, 116 out of 150. Sample 2 was 29 out of 148. Change the alternative so that sample 1 is bigger than sample 2. Hit compute. We see that we get all the same information, right? There's the difference between the two. Here's our z-stat, and there is our p-value. Okay, so all 3 ways we see that we definitely reject. Now, what if we wanted to test the claim by constructing the appropriate confidence interval? Well, that's really easy with technology because we can see very quickly how to do it in StatCrunch. Go to our options and edit, and all we're going to do is go back here, and instead of doing hypothesis testing, we're going to do a confidence interval. And remember, our alpha was set to 1%. Now, this is an upper tail test, right? We wanted to know that P1 is bigger than P2. So it's a one-tailed test. We want 1% up in that one tail. So that means the confidence interval is only 98% wide. That's where kids make the mistakes, is they think that they set this to 99, and your confidence interval is not always 1 minus alpha. You have to be careful. If it's a two-tailed test, right? If our alternative was not equal to, then yes, then that means half of our alpha would go in the upper tail, half the alpha would go in the lower tail, and then we would have 99 in between the two. But because this is a one-tailed test, all 1% goes in one tail, and the confidence interval is always centered at the origin, and it can't go into that critical region, so it has to stop with 1% above it, which therefore makes 1% below it, and it's only 98% in between. We compute that, and we can see that we get the same result if we interpret it correctly. We have a lower limit of 0.46, an upper limit of 0.6, almost 8 or 9. It doesn't really matter because both of those numbers are positive, which means the interval never contains 0, which means we can reject the null hypothesis again. If we want to use our calculators, we go back into the stat, over to tests, scroll all the way down. You start to see under the test, you start to get intervals, right? And we go to 2 proportions z interval. All of our information is there because from the last one we did, we obviously have to go down and change our confidence level to 0.98, right? Because it's the same idea of what's the width of our interval, not our alpha level. Calculate. And there we get the same things we got out of StatCrunch, right? Almost 47, almost 69%, both positive, so therefore we know we can reject the null hypothesis. If you were going to do it by hand, you would have to use this formula. Remember that your z-score is going to be alpha over 2, because when you do the confidence interval, right, you have to cut it in half, but that's only for a two-tailed test. In this case, because it's a one-tailed test, you're really doing z of just 1%. You're figuring out what the z-score is that gives 1% above, and then therefore also 1% below. So depending on your table, you're either going to look up z of 1%, or most likely your table is a cumulative thing. So you're going to look up z of 99% and get that z-score. Then you're going to plug in your p hat and q hat for the first sample, and then you're going to divide that by the sample size, n1, right? And then p and q2 over n2, take the square root, do a lot of math. That's going to give you an answer, and then you add that and subtract that from the difference between the two p's, right? This number right up here, this 77 minus 19 stuff. And that'll give you the lower and upper bounds that we saw in technology. That'll give you those, it's like 0.467 and 0.687. And then from that interval, again, you reject because it doesn't contain 0. All right, that's how to tackle questions with two proportions when you're doing hypothesis testing.